All right, guys, so this is 1.3 about inverse functions. If you're in honors class, you are completing this on the day that I'm absent, so make sure that you pause the video and slow it down and rewind as you need to and write down any questions that you have for me to answer when I come back. So inverse relations. The inverse of a relation, the notation we're going to use is written as, so the inverse of a relation R, if we had relation R, the inverse would be R with little negative 1. That doesn't mean like to the negative first power. It's just like the notation that we use for the inverse function. To find the values of an inverse relation, you're going to switch the x and the y values and then resolve it for x. Okay, one-to-one relationship. So a function has a one-to-one relationship if the relation and its inverse are functions. So if both are functions, then you can say that it is a one-to-one relationship. The way that we inverse the function would be switching all of the x, y points, because it says to switch the x, y values up here. So pause if you need to and write everything down. So for some examples, I gave you a relation R, you're writing the inverse relation. All you're doing is switching the x, y values. So 1, negative 2 becomes negative 2, 1. 2, 4 becomes 4, 2. 3, negative 1 becomes negative 1, 3. 4, negative 2 becomes negative 2, 4. That's it for the inverse relation. And the question, is R a function? Is this a function? Remember, our definition of a function is that x does not repeat. So is R a function? Yes. Is the inverse a function? No. The reason it's not is because negative 2 is repeating right here for the y value. So the inverse is not. So is it one-to-one? No, because both have to be functions in order to be a one-to-one function. Okay, number 2, you have your relation. We're going to inverse it by flipping all of the x, y values. So 5, 1, 6, 1, negative 4, 3, 9, 4. Is the regular original relation a function? No, because 1 is repeating right here. So we're going to say no. Is the inverse a function? Check all your x's. Yes, it is. It doesn't repeat. Is it one-to-one? No, because they're both not inverses. Last one, we have a mapping diagram. So what I did was I wrote out the original points just to kind of help me answer these questions here. So 0, 6, 1, 2, and 11, 6. And also it helps me find the inverse. So 0, 6 becomes 6, 0. 1, 2 becomes 2, 1. 11, 6 becomes 6, 11. Is the original a function? Yes. X is only pointing to one y. Is the inverse a function? No, because 6 is happening twice, so no. So therefore it's not one-to-one. All right, so let's talk about the horizontal line test. So just to recall, the vertical line test is used to determine whether the relation is a function, and the horizontal line test can be used to determine whether the inverse of a relation is a function or not. So we only use both if it's asking you if it's one-to-one, okay? So again, you're only going to use both if it's asking you if it is a one-to-one function. If it just asks you, is it a function, you're just going to use a vertical. But one-to-one function, you need to check vertical and horizontal. So example 4, check it will pass the vertical. It will also pass the horizontal. So this is one-to-one. This is an example of a trig function. It would pass the vertical, but it would not pass the horizontal. So no, because it fails the horizontal line test. Next page. So actually solving and making an inverse function. So the inverse of a function f of x is written as f negative 1 of x, because again, we're using that inverse function. This is very similar to before when this was our relation inverse. This is our function inverse. So to find the inverse of a function, step 1 is to replace f of x with y. Step 2, switch x and y. Step 3, solve for that new y. And then step 4, rewrite y as this inverse notation. Okay, so I'm going to do the evens here, and I want you to pause the video to do the odds. And then I will show the answers for the odds, but not walk you through all of the steps. So if you do have a question about one of them, we'll talk on Friday. So number 6, so first step, literally follow these steps, guys. Replace f of x with y. So this first thing is just y equals 5x now instead of f of x. Step 2, interchange x with y. So switch x and y. Step 3, solve for y. So how would I solve this for y? I would divide by 5. So x divided by 5 is equal to y. And then rewrite y as the inverse function notation. And that would be your answer. So it's pretty simple. Again, I'm going to leave you 7 to do. If you want to pause right now, you're welcome to. 8. So step 1, replace f of x with y. Step 2, switch x and y. And then step 3, solve. First thing I would need to do is multiply this side by 3 to get it off the bottom. So I'm going to multiply this by 3 and get 3x equals y minus 8. And then I need to add 8. So I get 3x plus 8 equals y, and then I rewrite with my inverse notation. Okay, number 10. So there is a domain restriction happening here because of what we're going to do and what we're going to see in a moment. Because it's just, if you graph this, it will be a parabola, but then its inverse won't actually be an inverse function. It won't work. So we have to just restrict the domain so that the inverse function does work. So again, replace f of x with y, switch x and y. I would add 9. And then how do I undo a square? I square a root. And then I replace it with the inverse notation. So you get this. All right. So we cannot have a negative under a square root. Now 11 is a little different because it's a cube root. You can have a negative under a cube root, but we cannot have a negative under a square root. Because if I square a number, it will always be positive. So we have to restrict the domain to what is greater than or equal to 0. So if I put negative 9 in here, then I will be greater than or equal to 0. So I just restrict that domain by saying x is greater than or equal to negative 9. So again, that is a domain restriction stipulation for square roots, fourth roots, any even roots, because I cannot, if I square a negative number, I'm going to end up with a positive. So I have to have the domain restriction. You will not have a domain restriction on number 11. Okay, so pause the video if you've not done so, 7, 8, or 7, 9, 11 for me, and come back to the video and see how you did. Okay, so hopefully you did that. Rewrite y. We would add 7 here, replace y with f inverse notation. Okay, write y, switch x and y, solve, so I would minus 1, and I would multiply by negative 5 over 2. So you end up with negative 5 over 2x plus 5 over 2 equals y, and then function notation. No domain restriction here because x is getting multiplied to that 5/2. It's not on the bottom of a fraction. All right, y equals, switch, add 6 first, cube root, so cube root x plus 6, minus 4 on the outside. And again, there's no domain restriction here because it's a cube root. All right, now we've talked about using compositions in the last section. This is the honors section for notes. The rest of you are still going to continue to the next page, but honors, you're going to specifically try this section. So to verify inverses, if f of g of x equals x and g of f of x equals x, then you have true inverses. So it's a way for you to verify. The question on the EOC might say, are these inverses? And instead of having to walk through inversing f and then inversing g, you can do the composition, put them inside each other, and make sure that they both equal x, and that means that they are inverses. So we did this in the last lesson. I'm putting the g of x inside the f of x spot, so this g of x will go here where x is, it gets squared, and you tack on a plus 8. So if I square that, the square root will go away, minus 8 plus 8 goes to 0, so we do end up with an x. We also want to verify the second one, so inside g of x, I'm going to put the f of x, so under that square root goes x squared plus 8 minus 8. Plus 8 minus 8 makes a 0, Square root x squared gets you x. So yes, they are inverses. All right, number 13. So again, I'm putting g of x inside f of x. So this whole thing has to go right here for x. So -4 multiplies to that whole g of x plus 5. This will make a negative x, and also we would distribute the 4. So this would make a negative x because the 4's would cancel. This would make a plus 20. So we get negative x plus 20 plus 5, but that gets me negative x plus 25, not single x that I needed. So they would not be inverses. So it's just a way for you to verify. All right, now graphing inverse functions. So given triangle ABC is formed by the points in the relation, what's the inverse? Graph ABC and its inverse, what do you notice about the graphs? So you're going to graph these points. What's the inverse? Well, remember, inverse is just switching the x and the y around. So the inverse is 6, -1, 2, -7, -3, 5. So I'm going to graph both. Okay, so my peach kind of color is my first. My green kind of color is my inverse. And what do you notice? Hopefully you notice that they are reflections of each other, and more specifically, they are reflections of each other in the y equals x line. And this is true for any inverse function. They should be reflections across the y equals x axis. That's this axis right here. And if they don't reflect across it perfectly, then you do not have an inverse function. So it's another way of verifying, a little bit easier for some people than algebraically. So find the inverse, then graph and verify the inverse relationship on the graph. So you can use Desmos to help you. This is a linear function. And remember, we write y, we replace y, we switch x and y, and then we solve. So I would need to -8 divide by 2. I then just simplified it down to a y equals mx plus b, because this is y equals mx plus b, it just looks a little funky. So we replace y now with the inverse. This would be 1/2 x. This reduces to a -4. So I'm going to graph this. My y-intercept is at 8, and then my slope is 2, so up 2 over 1. This one, my y-inverse is -4. My slope is up 1 over 2. And so you graph, and they should be reflections of each other. So yes, they are inverses. Again, you can use Desmos to help you. Plug this straight into Desmos, plug this into Desmos, grab a couple points, and put it on your graph. I'm fine with that since you're going to get Desmos on every question on the EOC. All right, go ahead and try 15 and 16 and come back to the video and see how you did. So 15, again, y equals, well, you should do y equals, I just switched my x and my y first, but y equals 1/3 x minus 1. Then switch x and y, then I added 1, then I multiplied by 3, but both parts get multiplied by 3, keep that in mind, and replace the y with the inverse, and then I graphed 1/3 x minus 1 and 3x plus 3. They are reflections. And then for this one, you have a parabola, but you're only talking about the positive part of the parabola, so don't go into the negative left side of the parabola, just stay on positive when x is greater than 0. So we would put y equals, switch x and y, so I end up with x equals y squared minus 4. I'm going to add 4, square root, and replace with inverse. Also, you need to write what the restriction is. So the restriction would be x needs to be greater than or equal to 4 because, again, it can't be a negative under a square root. So if I were to graph these, this is what they will look like. My peach, again, is that original, and I'm only talking about this part of it. So when you do graph this in Desmos, it will give you the whole parabola, but they have put the restriction right here and your notes on it, so we can only graph the part that's positive, where x is positive. And that's what makes these two work as inverses. Okay, so that's it. That's the end of 1.3 notes. Record any questions that you had, and then work on the digital activity for inverse functions to get some practice.